Okay, so I thought I had gone far enough in that last video and decided to save on page 567, chapter 20, standardized practice test. We're now going to do problems 8, 9, 10, and 11. And I hope you guys are enjoying the problem solving skill that you're learning while we do this. I hope that you're enjoying the application of static electricity, even down at the atomic level. We're talking about things. And we're going to continue now with problem number 8 on page 567. I love you guys, and I'm having a lot of fun. I wish you were here with me. I miss you, and looking forward to seeing you guys again soon. An alpha particle has a mass of 6.68 times 10 to the minus 27 kilograms. Okay? So an alpha particle has a mass of 6.67 times 10 to the minus 27 kilograms. All right? Now what is an alpha particle? Well, there are two neutrons that I'll draw in black and two protons that I'll draw in red. I meant for all four of those circles to be about the same size. It looks like the protons are bigger than the neutrons the way I've drawn them, but they're actually about the identical diameter and identical mass each. And an alpha particle, so this has a 2 plus charge. 2 plus as far as the, what's that called? It's called the elementary charge. So the charge on a proton has one elementary charge positive. Charge on the other proton has one elementary charge positive. Of course, neutrons are neutral. They do not have electric charge. And so you have 2 plus. This is very similar to what you do when you have, like, say, an OH minus, right? With a sodium with a plus, because the one electron left the sodium and came over here to the hydroxide ion, and they dissolve in water. So you end up with a sodium plus ion and a hydroxide ion in water. Okay? Everybody follow that logic? Sodium hydroxide. All right, so the question is, an alpha particle has a mass of that and a charge of 3.2 times 10 to the minus 19. So is that twice the elementary charge? It is, I believe. I think the elementary charge is 1.602. So this is 3.2 times 10 to the minus 19 coulombs. This 2 plus. All right? So there you have it. That's a positive charge as well. Okay? So there's 2 times the elementary charge. Instead of it being this is basically 1.6 times 2. This is the mass of a proton or a neutron times 4. Right? All right, here we go. What is the ratio of the electrostatic force to the gravitational force between two alpha particles? All right, so that's a detail of an alpha particle. Now, we're going to drop it down to a particle. There's a particle, and there's a particle. And this is an alpha particle. These are alpha particles. All right? They have a mass of that and a charge of that. So what is F sub G divided by F sub electrostatic force? What's that equal to is what we're being asked to solve for. Well, F sub G is equal to G M1 M2 divided by the distance squared. And that's divided by, that's F sub G, here's F sub E. K times Q1 Q2 divided by the distance squared. Look at that. We don't even need to know what the distance is between these two particles. It doesn't matter because d squared goes away. Did everybody follow that algebra? All right. So now we just need to continue plugging in. What's G? Anybody remember what G is? It's given in, I think it's like 9.0 times 10 to the ninth. Let me remember that. It is, yeah, 9.0. I'm going to move to the side over here. 9.0 times 10 to the ninth. And that has some fancy units, right? That has units of Newton meter squared per Coulomb. Can't even draw a C. Per Coulomb squared, right? So that's G times M1, which is 6.67 times 10 to the minus 27 kilograms. And M2 is 6.67 times 10 to the minus 27 kilograms. All right, so that's the mass of the two alpha particles. And G, oh, I'm sorry, that's not G. I goofed that up. This belongs to the denominator. That's K. I blew that one. That's K. That belongs here. 9.0 times, let's see, it's 10 to the ninth, I believe. I want to make sure. Yeah, times 10 to the ninth, Newton meter squared per Coulomb squared, right? I got to remember what G is now. I'm going to go to the back flap of the textbook. I'm going to look up the gravitational constant G, and it is 6.67 times 10 to the minus 11. Okay? 10 to the minus 11 Newton meter squared per kilogram squared. Right? So this is a meter, that's a meter. Everybody follow that? Okay? So we're still talking about, now let's keep plugging in for Q1 and Q2, which is 3.2 times 10 to the minus 19 coulombs and 3.2 times 10 to the minus 19 coulombs. Q1 and Q2 are the same, two alpha particles with this charge. All right? So you can see that meters squared and newtons go away, and coulomb squared goes away with coulombs, and kilogram squared goes away with kilograms, and we have a unitless ratio, which makes perfect sense. F sub G divided by F sub E is a unitless value. Let me make sure you can see what I'm working on over here. All right. So I crossed out my newtons, my meters squared, my kilograms squared, my coulombs squared. Crossed those out, and now I have a unitless ratio. So now I need to do the math. All right? And for that, I'm going to use a calculator and my head. On. All right. This is G, 6.67 times 10 to the minus 11. So 6.67 times, now moving on. Interesting. That's 6.67 times 10 to the minus 27 kilograms. I didn't notice that before. 6.67 times 6.67. All right. And now I need to divide by 9. I divide by 3.2 twice. And I get 3.2. 3.2 times, and now let's add this up. This is minus 11, let's do, 11 plus 27 plus 27 equals, that's negative 65 here in the numerator. Let's see what the denominator is. Clear. That is 9 minus 19 minus 19 is minus 29 in the denominator. So it actually is a clear. I've got now minus 65 in the numerator, right? So that's 65, and then this is a minus 29. So I need to change the sign. So clear, I need to say 29 minus 65, actually, to get that correct. This is 36. This is 3.2 times 10 to the minus 36. All right, and that is the ratio between the force of gravity of two different alpha particles, right? Here's the first alpha particle, here's the second alpha particle. Two different alpha particles. There's a gravitational force divided by the electrostatic force. I don't need to know what the distance is because that goes away. I was given Q for each alpha particle. I was given M for each alpha particle, and these are lookups. K and G are lookups. So I was able to do the math, and I got 3.2 times 10 to the minus 36. Let's see if that's one of the answers. Page number 570 something, if I'm not mistaken. Almost there. 567. The ratio is, they say it's 3.1 times 10 to the 35th. Wonder how I got that wrong. I got 3.2 times 10 to the minus 36. Let's do the math. See where I messed up. All right, I've got 10 to the minus 11. 10 to the minus 27 and 10 to the minus 27. That's right. Did I do that right? Yeah, that's right. Oh, there's a 6.68. I see the mass number should have been an 8. That's one thing. That's why I got 3.2 and they got 3.1, I'm sure. The mass is equal to 6.68. So that should be a 6.68. And this should be a 3.1 then. All right, so that makes sense. Now, why did I not get minus 35 like they did in the book? Let's check it one more time. It could be the book is wrong. Let's check. All right, so this is minus 11. We're going to find a negative number. We know that. So I'm going to flip my negatives to positives so that I can get that done. 11 plus 27 plus 27, right? Now this is a positive, so I need to flip it to a negative, and I'm dividing it, so I need to go plus 9. And then this is a negative, and I need to subtract 19, minus 19 minus 19 equals, I get 36. So maybe this is 31. Let's do the math one more time. Clear. 6.68 times 6.67 times 6.67 divided by 9 divided by 3.2 divided by 3.2 equals, I got 3.2. 3.2 times 10 to the minus 36. That's what I get, you guys. I don't know why the book says 10 to the 35th. I think the book is wrong. I think it's 3.2 times 10 to the negative 36. Or they say positive 35. I don't see, oh, I bet they flipped these. But even so, if they flip those, I don't see how you get, let's see what happens if we flip those. That's what's going on here. They're looking for, no, I don't see how we couldn't get an inverse. Let's see what the inverse is of that. No, I don't think so. I don't see how they got what they got. The ratio of f sub g per f sub e is equal to 3.2 times 10 to the minus 36. What is that? Is that, oh, I bet if we do invert it, we'll get the right answer. Let's see. How do I do a 1 over x with this crazy calculator? Okay, 3.2, where's my 1 over x function? Clear, I'll just do a 1 divided by 3.2. That is a 3-1. Now, oh no, that's 0.31. Yeah, I get it now. They figured out f sub e over f sub g, and they got 3.1 times 10 to the 35th, and that's correct. Okay, because the inverse of 3.2 is 0.31. So to move the decimal place to 3.1, you have to get to 10 to the 35th. Okay, everybody see that? All right, I'm not going to do it again. I have the right answer. They have another right answer in the book, and that's okay. They figured out f sub e over f sub g. Now, I want you to notice the power. This is huge. This is an enormous number, the ratio. Okay? 3.1 times 10 to the 35th. So that's why people say the electrostatic force is greater than the gravitational force, because when you, in most scenarios, when you do the ratio of the two, you're going to get that number 3.1 times 10 to the 35th. I'm going to do it like this. I'll show you this way. So that means that f sub e divided by f sub g is equal to 1 over 3.2 times 10 to the 36th, right? 10 to the negative 36, and that is equal to 0.31 times 10 to the positive 36, and that's equal to 3.1 times 10 to the 35th. Okay? So this ratio is something, that's something. And what that says is that the force of the electrostatic force is enormous. 10 to the 35th. That's enormous in terms of order of magnitude, that ratio. Okay, just wanted you to understand that. Number 9. Charging a neutral body by touching it with a charged body is called charging by, so we're touching. So we're charging a neutral body, so it has 0 charge as we start, and now we touch it with something, with a charged body, and that's called charging by conduction. Number 9 is A, conduction. Okay? Number 10. Macy rubs a balloon with wool, giving the balloon a charge of negative 8.9 times 10 to the minus 14 coulombs. What is the force between the balloon and a metal sphere that is charged to 25 C and is 2 kilometers away? Shoo! Woo! Okay? This is just another application of Coulomb's law, and you're assuming that the only two objects in the universe are the balloon and this metal sphere. And that's it. Those are the only two objects in the universe, and there's this balloon that has a certain Q1, and there's this charged metal sphere that has a certain Q2, and they're 2 kilometers away. Now I want you to notice 2 coulombs is an awful lot. You'll notice all the problems that we've been doing have been talking about 10 to the minus 6 coulombs, 10 to the minus 9 coulombs, and less and more. But that's basically, I mean, you know, 2 coulombs without that 10 to the multiplied by 10 to the minus 6, that is a lot of electrons. I'm here to tell you. All right? I just want you to know. That's a hard thing to do, to charge something to 2 coulombs. Okay? It's possible, but it's hard. It's the kind of thing that might be discharging electricity and you just can't get there. Okay? But this is the word problem they gave us, and we're going to act like those are the only 2 objects in the universe, including yourself, even though you have to be there in order to do the calculation. All right. Macy rubs a balloon with wool, giving the balloon a charge of minus 8.9 times 10 to the minus 14. Can you see this board? Yes. I'll do it over here on this board. Come on. The cap's not coming off. Here we go. This is good. So here's a balloon that Macy has made and charged it up. We'll call it a helium balloon. It floats. It's lighter than air. All right? So this is Macy's balloon. And now over here, 2 kilometers away, hopefully on a high tower, it has 2 coulombs of charge. Right? So this is Q2 is equal to 2 coulombs. D is equal to 2 kilometers. Sorry, I didn't do that again. D is equal to 2 kilometers. Okay? All right. So we've got Macy with her balloon. What's her balloon's charge? Q1 is negative 8.9 times 10 to the minus 14 coulombs. All right? Now, so this is 2.5 times 10 to the 13th coulombs more than that. Just so you know. All right. So the question is, what is the force, right? What is the force between the balloon and the metal sphere? So how hard is Macy having to pull back? Because this is negative and this is positive, and these are attracting each other. So the question is, how hard is Macy having to pull in that direction, or how hard is the balloon attracted? What is F sub Q2 on Q1? Okay? That's what I'm solving for here. And that is F sub Q2 on Q1 is equal to K times Q1 times Q2 divided by the distance between Q1 and Q2 squared. And that's equal to, let's see if we can make it all fit, 10 to the 9th, and that is Newton meters squared per coulomb squared. And then we've got two different coulombs. Here's 2 coulombs times 8.9 times 10 to the minus 14 coulombs. All right? And then we got to divide that by 2 kilometers. 2 kilometers. We need to change that to meters. That's 2,000 meters. And that's squared. Okay? Everybody follow that? Can you see it? Not quite. Yeah, you can. I'm over here. Now I'm hiding it from you. Okay? So now we got it. We're ready to do the math. Okay? At least I am. Hope you are too. Here we go. 9 times 10 to the 9th. Clear. On. Clear. 9 times 2 times 8.9 divided by 2,000 divided by 2,000 equals, there's a lot of zeros in this number, but it's basically 4. It is a 0.000, 1, 2, 3, 4, 4, and then it's not worth mentioning, okay? So 0.00004 times 10 to the something, okay? And what is that 10 to the something? That is 9 minus 14, or 10 to the minus 5, right? So the pull on this balloon between these 2 objects, and they're the only 2 objects in the universe, is equal to, the electrostatic attraction force is, we can move this, 1, 2, 3, 4, 5. It's 4 newtons. Okay? Which is not insignificant. 4 newtons is not insignificant, right? It would probably motivate the balloon, even though it's 2 kilometers away, that would motivate this balloon towards this object. Okay? 4 newtons of force, even though you're 2 kilometers away. 2 coulombs is a big deal. A lot of electrons in one place. Actually, that's a positive 2 coulombs. So it's actually a lot of electrons missing. That's what it is. It's a lot of missing electrons for one place. Okay? Is that one of the answers? We did number 10, and we found out that it was 4 newtons. You know, that's not one of the answers. I wonder why not. Macy rubs a balloon with wool, giving the balloon negative 8.9 times 10 to the minus 14. Let's put a negative there. I don't think we're supposed to. I'm sure we're not supposed to. I mean, it doesn't matter whether the force is negative or positive. You decide what direction it is from the picture that you draw based on the charges of the objects. So 9 times 2 times 8.9. Did I do that wrong? Divided by 2,000 twice? Clear. 9 times 2 times 8.9 equals divided by 2,000 divided by 2,000 equals 1, 2, 3, 4, 5. I got 4. 0, 0, 0, 0, 4. And this is definitely times 10 to the minus 5 here. And I move the decimal place 5 places, and I get 4 newtons. Boy, I don't know what the book's talking about for problem number 9. I'm sure I got it right. Or 10, I mean. I'm sure I got number 10 right, and the book is wrong. there should be an answer called 4 newtons. Isn't that interesting? What are their answers saying? 2 coulombs. All right, A is too small. 8.9 times 10 to the minus 15, no way. 5 times 10 to the minus 9. That seems unreasonable to me since I got 4 newtons. 2 times 10 to the minus 12. Still seems unreasonable to me. I bet they thought this was a couple things. I bet they didn't convert 2 kilometers to 2,000 meters. But still they don't have a 4.0 anywhere. So that's strange to me also. All right. I don't think I did anything wrong. If somebody can figure out what I did wrong, let me know. There will be some sort of a prize. I don't know what that prize will be yet. Number 11. According to the diagram, what is the net force exerted by charges A and B on charge C? Okay, does everybody see the diagram? So what we're going to have to do there is use the Coulomb's law to figure out what the charge is between A and C, okay? Or obviously the force between A and what is the force on C from A, and what is the force on C from B? And you'll notice their distances are a mirror. A and B are both 0.3 something away from that x-axis, right? And 0.4 is the x distance C from the y-axis, okay? So you can figure out the angle of each of those 2 forces, and you can multiply by cosine theta, okay, which is 0.4 divided by 0.3, right? Cosine theta is 0.4 divided by 0.3 in each case. So the force times 0.4 divided by 0.3 between A and C, and the force between B and C, so there's a net force probably in the, let me see, minus 2, so they're the same charges. All right, so there's a force towards the y-axis is what it is. From C towards the y-axis is what it's going to be, and you can figure out what that is because, no, this is repulsed, they're all repelling. So it's going to be away from the y-axis, forgive me, away from the y-axis. Let's do the problem. Here we go. All right. I was thinking about not doing the problem, but we're going to do the problem, and I'm only going to know that you followed me on this video and watched it and learned if you write down what I write down here now, okay? So problem number 11. I'm going to throw this marker away. Problem number 11. This was a long standardized practice test, wasn't it? According to the diagram, what is the net force exerted by charges A and B on charge C? So here is charge A, and here is charge B, and here is charge C. And we know that this distance is 0.4, and this distance is 0.3. And we do not know what the units are. Did you notice that? They didn't give us units. They just said that it was 0.3 and 0.4, the relative distances. Okay? Now we're given A is -2 microcoulombs. Okay? We'll learn a little bit more about what that says. This also is -2 microcoulombs. Now that's handy because these distances are the same. Okay? And so the force created, this guy is -4 microcoulomb. Okay? So the force created here and the force created here, this portion of the force and this portion of the force of this force cancel. So F net is only going to be in this direction. All right, and it's going to be 2 times the force in that direction. So luckily we only have to do this problem once. F is equal to K Q1 Q2 divided by the distance squared. Okay? And we're going to know, and then we're going to have to, and we know, so we'll know that's the magnitude of that force. Okay? And then we can figure out what the force is here. And then we know the force here is being countered by that one, and so we'll just have another one of those added on that particle. That particle is being pushed up and down the same amount, and it's being pushed to the right the same amount, so it's just 2 times that amount. Does that make sense? The force to the right. All right, so this is equal to 9.0 times 10 to the 9th, and that is newtons meter squared per coulomb squared. All right, and this is Q1 is -2 times 10 to the -6 coulombs. Okay, that's what that mu, that micro means. 2 times 10 to the -6 coulombs. Okay, and this is 4 times a -4 times 10 to the, that's microcoulombs, 10 to the -6 coulombs. All right, and then we've got the distance between these two objects squared. Okay, so what is that distance? Well, that distance is a squared plus b squared, the square root of that, the quadratic equation. So I'm going to just do that. The square root of 0.3 squared plus 0.4 squared. That's the distance, and that has to be in meters, but it doesn't matter whether it's kilometers or meters or whatever, because this ratio is what drives that distance. Okay, and then we're going to square that. Everybody follow? So the distance between this particle and that particle is the hypotenuse, and we have to square it. All right, and we have to assume that this is meters. We can't assume it's kilometers, now that I think about it, because if it were anything other than meters, then that would not allow us to cancel these meters squared. So it is pertinent that these are 0.3 meters and 0.4 meters. Okay? You can't have it be kilometers or centimeters or whatever, because this has units of distance in it that have to be met in order for it to cancel. So I have to make an assumption. Oh, I see it's in meters. You see that the y-axis has a parenthesis in meters, and the x-axis has a parenthesis in meters, so it is in meters. Okay? So be it. Are you ready? Here we go. So, the ultimate force we're looking for is 2 times that. F total is 2 times this, and then we've got to take the times the cosine of the angle, or 0.4 divided by 0.3. Okay? And then we have to take this and multiply that by 2. 2f, 2 times that. And 2f cosine theta. We'll put cosine theta here. So here's our cosine theta. All right? Here we go. On. I am ready now. 9 times 2 times 4. I guess I'm not ready. Clear. What do we got here? I've got to figure this out first. All right, so 0.3 times 0.3 equals 0.09. 0.4 times 0.4 is 0.16. So that is 0.25. So 0.25 square root. Well, that's 0.5. All right? And then 0.5 squared is 0.25. So this, in the denominator, becomes 0.25 meters squared. Okay? And this in the numerator we can figure out now, or we can figure out how to proceed. By the way, these meters squared go away. These coulombs squared go away, and we're going to end up in units of newtons. Clear? Are you ready now? I was ready a while back, but I wasn't really, was I? 9 times 2 times 4 times 0.4 divided by 0.3 divided by 3 times 10 times 2 divided by 0.25 equals 768, and this is 10 to the 9th times 10 to the minus 3, 10 to the 9th minus 6 is 10 cubed, minus 6 is 10 to the negative 3. That's where I got that. 768 times 10 to the minus 3 newtons. Okay? And that would be 0.768 newtons. All right? So, can you see all that work? I think so. Hope you guys are having fun. Now that turned out to be a harder problem than I was imagining. And that's why I decided to go ahead and do it. Because I thought I could just explain it, but without explaining how I explained it, this force total is this force right here. Okay? And that particle's being pushed at 0.768 newtons away from A and B. Okay? All right, you guys. You know I love you. I've been telling you that for some time. So next, be looking for a video of the thought experiment where we're going to look at the forces involved on the inside of an atom, of a helium atom. We're going to look at the forces between the protons that are trying to fly apart. There must be a force holding those two protons together. We're going to learn the gravitational force. which is negligible compared to the electrostatic force pushing those protons apart at the nucleus of a helium atom. And then there's the 2 electrons in the cloud around the helium atom in the s orbitals that are available to the helium atom. And so we're going to be able to investigate what is the subatomic weak force. The force, so the subatomic strong force is the force that is holding those two protons together at the nucleus of the atom. And the subatomic weak force is keeping the electrons away. There's an electron negatively charged, 2 of them, flying around a helium nucleus. And now, why don't the electrons immediately collapse down to the nucleus? Why is it that the electrons continue to be in a cloud around a helium atom? Well, that's the subatomic weak force that's pushing them out. And the distances involved are so great that the weak force is way less, way less than the subatomic strong force. And those forces are very different. They're not the same thing. Scientists can't explain those forces at the inside of an atom any better than they can explain the force of gravity between mass, or the electrostatic field force between 2 charged particles. Okay? These 4 field forces are understood at a level that's better than my understanding of them. Okay? I mean, I'm not a physicist, I'm a chemical engineer, but we can do calculations using Coulomb's law and Newton's universal law of gravitation. We can do calculations because we know the distances and we know the relative charges and the masses. We know the masses of the neutron and the proton and the electron. So we can do these calculations concerning the helium atom. It gets more complex. We can do these calculations still with, say, a copper atom, but it gets more complex because there's more protons and neutrons that allow the copper atom to not fly apart. Okay, there's a ratio of protons to neutrons there in the copper atom that stabilize the copper atom with the electron cloud around it. But these same strong forces and weak forces exist inside the copper atom. And it's those same forces that keep the copper atom together, and we can't make copper atoms blow apart. We can make radioactive elements blow apart, as we have shown. That's called fission, uranium fission, but that's the biggest element. Uranium is the biggest element that exists in nature. Here's uranium, 92 protons. Uranium is the biggest element that exists in nature that, and we can take that element that exists in nature and we can make it divide by bombarding the atomic nuclei of the uranium atom with a neutron. You hit it with a neutron, boom! It gives off 3 neutrons. Those 3 neutrons go off to other uranium atoms, boom! Those all split, etc., etc. When you concentrate uranium 235 to a concentration that is great enough in a lump of uranium, then you can have a nuclear explosion that self-propagates. All right, that's called fissionable material. And U-235 doesn't go boom in nature because it's surrounded by mostly U-238. Okay, so anyway, talking about atomic fission, there's also atomic fusion, and we'll talk about that more maybe in a future video. And so anyway, I hope you guys enjoyed doing this standardized practice test. I hope you feel empowered to understand what electrostatic force is and how to make calculations associated with what is involved I mean, we were all over the place with these problems. Lots of great problems to work and understand the electrostatic forces that exist in nature. And we can talk about it all day if you guys want to call me at 317-527-9531 and leave me a message if I don't pick up. I love you, and I am praying for you, and I'm enjoying, the interaction at least that we can have at this day. God bless.